In this screencast, we're going to describe the two systems of units typically seen in fluid mechanics. Now, when you think of systems of units, you probably think of the International System, or SI system, in which we use meters for distance, kilograms for mass, newtons for force, pascals for pressure, etc. The other system that you're probably familiar with is the English engineering system. And you've seen these units before in terms of feet, miles, pounds mass, pounds force, psi, maybe inches mercury, etc. The two systems of units that we want to talk about here, so that we could get into this term dimensional homogeneity, is the FLT system of units, in which we refer to units in terms of force, length, and time, and the MLT system, where we refer to units in terms of mass, length, and time. So if we look at something like energy, where we know energy can be calculated as a force times a distance, that's all it is in the FLT system, would be E equals F times D. However, in the MLT system, we have to rewrite force in terms of mass and length. And we know that force can be calculated as a mass times an acceleration. We know acceleration to be a length per time squared. So if we put force in terms of MLT system, we're going to see that force is mass times a length divided by t squared. So then we could rewrite energy in terms of the MLT system, and this results in a mass times a length squared times t to the minus 2 in terms of its units. Now sometimes when you're working with equations and you get certain numbers that have these kind of strange units to them, one of in particular that I could recall is when you get to the units where it's length squared per time squared. And the first time I saw this, it didn't really click to me as to what kind of dimension that this was trying to describe. But if you work through unit analysis as such as we've done here, you could see that this is pretty much the same thing as the energy equation, but we've removed the mass. So this is equal to an energy divided by a mass, which is pretty common for enthalpy calculations, in which you might get something in terms of a kilojoule per kilogram, a specific heat of reaction or heat of formation of something could be reported in terms of kilograms. So just something to keep in mind when you're working through units. So when we talk about something being dimensionally homogeneous, we mean that the dimensions on both sides of the equation must have the same units. And in some cases, we can combine these numbers and get something that has no units. And this is called a dimensionless number. So we don't know necessarily what that value might be, but there's going to be no units associated with that. So we're going to practice this to determine if any of the following are dimensionless numbers. Now the first thing is to define each of the variables that we're using. You're familiar with F, that's going to be a force. P here is a pressure. A is an area. Rho signifies density. G is the gravitational constant. And we've written out volume and height. If we rewrite these, whether in terms of the MLT or FLT system, we could determine whether or not any of the following are dimensionless numbers. Let's start with the first one. For simplicity's sake, we'll use the FLT system. So we could just write force, and we know pressure is equal to a force per area, and area is a length squared, and then this is going to be times length squared. So we can see here that the length squared terms cancel and the forces cancel, and this is going to be equal to 1 in this case. So this is a dimensionless number. For the second system, force over pressure times rho, we could use the FLT system as well. We'll write force, again, over force per length squared, and then rho is a mass per volume, which is a length cubed. Now you can see here that although the forces cancel, this is going to end up giving us units and length to the fifth over mass. So this is definitely not a dimensionless number. The bottom left one, volume over the square root of the gravitational constant times height, we're going to go ahead and write this in terms of the MLT system. So volume can be reported as a length cubed. Now this is over the square root of the gravitational constant, which is an acceleration. So we'll write this as a length per time squared. This is to the 1/2, and this is going to be times a height. So length also to the 1/2. Now when we simplify this out, this ends up being a length squared times a time. So this also is not a dimensionless unit. The last one already has force in it, so we'll go ahead and use the FLT system to analyze this. This is going to be a force times a density squared, and we know density is a mass per length cubed. This is going to be squared, and this is over a pressure, which is a force divided by an area, which is a length squared. This simplifies down to a mass over a length to the fourth. So this is also not a dimensionless number. A dimensionless number can typically give us insight into the particular conditions of a system. For example, the Reynolds number, a very common dimensionless number you'll see in a fluids class, is the ratio of the inertia force to the viscous force of a flowing fluid. And we could calculate this as the density times the velocity times the diameter of the fluid flow over the viscosity of the fluid. And I'll leave that as an exercise to see how the units cancel out for those variables. Now, a value of 2100 marks a boundary between flow that is laminar in nature to one that is turbulent, something that has a Reynolds number higher than 2100. Thus, it's important when you calculate any of these known dimensionless groups that there are not remaining units after doing these calculations. Another thing you could get from dimensionless numbers is that if you know the units must cancel out, you could determine what the units would be for a variable that you may not be familiar with. For instance, a very common unit that's used for reporting the viscosity of a fluid is that of poise or centipoise. However, that doesn't necessarily fit in with our MLT or FLT system of units. So if we know the Reynolds number is dimensionless and we know the units of the variables on top, we could determine what the units of viscosity would be. And as you can see, it's going to be a mass per length times time, and in an SI system of units we may report that as a gram per centimeter second.